Welcome to the lecture series on numerical methods. In the current lecture series, we are discussing here numerical differentiation. In the last lecture, we have started this numerical differentiation using Lagrange interpolation method and divided differences. And in the end of the last lecture, I have just given one example based on this divided difference, that how we can use this differentiation. And there itself I have just discussed that how we can just apply the divided difference on the tabular form first, and then we can just go for this derivatives. And after this, we will just in this lecture we will just go for this maxima and minima of a tabulated function, then the error estimation in the differential equations. That this numerical differentiation, how it can be applied for this error estimation in interpolation polynomials. So, this present table already I have discussed in the last lecture, that how we can just find this first order difference, second order difference, third order difference and fourth order difference. If a tabular value is given to us like x equals to 1, 2, 4, 8 and 10, and then the corresponding y values are given as 0, 1, 5, 21 and 27 suppose. How we can compute this derivative of this function y at a point 3 suppose, and double derivative also at that same point. So, first we have to go for this divided difference table. Already in the last lecture I have derived this divided difference table there itself, and after that, once we are just using this divided difference table, we will have these values like first divided difference value, that as we have just obtained here as 1 here, second divided difference for the first table form we are just obtaining 1 by 3, then 0, then minus 1 by 144 here. So, if you will just use this divided difference formula, usually this Newton's divided difference formula is written in the form like P n x, this equals to summation of j equals to 0 to n, sorry, this is I equals to 0 to n if you will just write. Then we can just write f of x0, x1 to xi, then we can just write product of j equals to 0 to I minus 1 and x minus xj here. So, either you can just use this one as the call bracket we have used here. So, if we are just writing this polynomial in this form, then since the data it is just given to us are like x0, x1, x2, x3 and x4 here. So, if you just collectively write these data here like x0 equals to 1 here, x1 equals to 2 here, x2 equals to 4 here, x3 equals to 8 here and x4 equals to 10 here. Then we will have like 5 points here. This can just generate a polynomial of degree 4 here. So, we can just write this function f of x, it can be approximated with a polynomial of degree 4 here, p4x, and that can be written in the form like f of x0 plus x minus x0, f of x0, x1, x minus x0, x minus x1, f of x0, x1, x2 plus x minus x0, x minus x1, x minus x2, f of x0, x1, x2, x3 plus x minus x0, x minus x1, x minus x2, x minus x3, f of x0, x1, x2, x3, x4 here. So, if we will just put all these values here, since our initial values it is in a tabular form, it is just given us as like 0 here. If you will just see this tabular values here, so first corresponding value of x is just given here. If you will just see f0, it is given as 0, f1 as 1 here, f2 as 5 here, f3 as 21 here, f4 as 27 here. So if you just put these values, f of x0 is 0 here, so you can just write this one as a 0 plus x minus x0, x0 is 1 here, then f of x0, x1, this is the tabular form already we have discussed in the last lecture, that is especially written as 1 here, plus x minus x0, x minus x1 here, into the divided difference between this f of x0, x1 and x2. Collectively, if you will just see this table, so we can just we have already obtained that one the values as 1 by 3 here, plus x minus x0, x minus x1, x minus x2, that is as 4 here, into your f of x0, x1, x2, x3 here, and that value it is just giving you 0 there, plus x minus 1, x minus 2, x minus 4, x minus 8 into f of x0, x1, x2, x3, x4 in the arguments form, and that value is especially just giving us in the tabular form as minus 1 by 144. So if we can just multiply all these terms here, then we can just obtain this polynomial that is in the form of x only here. So obviously if this polynomial is expressed in the form of x, directly we can just apply the derivatives to get this differential form of this polynomial p4x here. So if you just take all these products here, then this product form can be written in the form like first term is as x minus 1 here, second term if you will just see here, so that can be written as 1 by 3 x square minus 3x plus 2, and since next term immediate term is 0 there, so then the last term it can be written as minus 1 by 144 x to the power 4 minus 15 x cube plus 70 x square minus 120 x plus 64 here. And if you will just take this derivative here, that is in the form of f dash x. So f dash x can be written as first derivative here 1 plus 1 by 3 into x square minus 3x plus 2, derivative is 2x minus 3 minus 1 by 144, then x to the power 4 is 4x cube minus 45 x square plus 140x minus 122 here. So final form we are just obtaining here f dash x as 1 plus 1 by 3 into 2x minus 3 minus 1 by 144 x to the power 4, sorry, I will just write this one only the derivatives. So that is why 1 by 3 into 2x minus 3 minus 1 by 144 x to the power 4 minus 15 x cube then plus 70 x square, 70 x square means the derivative will come as 140 x here, then the last term is minus 120. So if you want to find suppose this derivative at the point 3 here, so directly we can just replace this x by 3 here and we can just obtain this derivative at the point 3. And if we want to evaluate this second order derivative here, then directly we can just differentiate once more here, that is first term is 0 here, then 1 by 3 into 2 minus 1 by 44, then this is 4x cube minus 45 x square plus 140. And similarly if you will just put here f double dash of 3 then we can just obtain the second order differentiation of this fourth order polynomial at the point 3 there. So obviously this values, if it can be calculated, so that can be represented in the form of f dash 3 equals to 1 plus 1 by 3 into 2 into 3 minus 3 minus 1 by 144 into 4 into 3 cube there. So especially it is just it should be like 4x cube minus 45x square, if you will just see. So this should be 4x cube minus 45x square, if you will just take the derivatives. So then it can be multiplied and we can have the clear form here. Then it will just change to this is like 12x square, this should be like 90x here, and it is like 140. So if you will just directly put this f double dash of 3 here, then we can just obtain this value as 0.81944 here. So then we will just go for this computation of maxima and minima using this polynomial differentiation. The beauty of this method is that even if the function is not known to us, then we can have this maxima or minima of this function if the prescribed tabular values is given to us. So we can just use this same arguments form of x here, and we can just determine this maxima and minima for this tabulated function by differentiating this interpolating polynomial here, and maxima and minima of y equals to f of x can be obtained by equating dy by dx equals to 0. And first, if you will just use Newton's forward difference formula to compute this maxima and minima for the tabulated values, then the formula can be written in the form like the formula for this Newton's forward difference formula. Already we have discussed this one in previous lectures, and if I will just write once more here, then this Newton's forward difference formula can be written in the form of y of p or y of xp or y of x. This can be written as y0 plus p delta of y0 p into p minus 1 by factorial 2 delta square of y0 plus up to p into p minus 1 up to p minus n plus 1 by n factorial delta to the power n of y0 here. And if you just differentiate this one with respect to p here, so then we can just obtain dy by dp as del y0 plus 2p minus 1 by 2 factorial delta square of y0 plus all other terms there. For maxima, if you will just put here dy by dp equals to 0 suppose, so this can be written as a 0 here. This implies that we can just terminate this left hand side series expansion up to certain terms, then we can just obtain this maxima or minima of a function. Suppose if the left hand side is just truncated after suppose third differences for our convenience suppose, then we will just obtain a quadratic equation here in p, and which gives two values of p, since it is just a quadratic equation here corresponding to these values of p, then we can have a maxima or minima at that point. And once we have these values of p there, then we can just obtain this value of x at that point, since usually this x can be written as in the form of x equals to x0 plus ph here, or for convenience we can just write sometimes if x0 equals to a is a particular value, then we can just write this one as a plus ph here. And once this values of p is known to us, then we can just determine the values of x, and if the x is known to us, then we have to see these tabular values that where this x is placed inside this table, and at that point either this forward difference formula or backward difference formula can be applicable, that we have to check. And once we can just check that one, since that depends on the values of p at that point, So, once we are just obtaining the values of p at that point, then we can just obtain the values of another y at that point for these values of y of x. And to obtain this maxima or minima, the usual criteria is that we have to see that for maxima we have to put d square y by dx square is negative, and we have to show that for minima d square y by dx square is positive. Suppose we have an example here that the question is asked to find x for which y is a maximum, taking the difference of two second order from the following table and find maximum value of y. And if I will just consider this table here, like x values are prescribed as 1.2, 1.3, 1.4, 1.5 and 1.6 with space size h equals to 0.1 here. Suppose the tabular values are given at x equals to 1.2, 1.3, 1.4, 1.5, 1.6 here, and the corresponding values of y are given as 0.9320, 0.9636, 0.9855, 0.9975, and last value is given as 0.996. And the corresponding values for forward difference formula or forward difference table can be given as the difference of these two. So, that is just given as 0.0316 here. If we will just take the difference of these two here, so the values can be written as 0.0219 here. If we will just take the difference of these two here, then that will just give you 0.0120 here. If you will just take the difference of these two here, that can be given as 0.0021. Then the second difference for these numbers can be written as minus 0.0097, first one. Then second one, it can be written as minus 0.0099. Third difference, it can also be written as 0.0099 here. Sorry, this is del square. Then we will just go for del q of y here. And if you will just take the difference here, so the first difference, this will just give you minus 0.02 here, and this will just 0 here. And fourth order difference, you can just write this one as 0.002 only. And the space size, if you will just see, these equidistance points are there, so that is why h can be written as 0.1 here, and starting value for y0, it can be written as 0.9320 here. And based on this, if we want to determine this interpolating polynomial, the interpolating polynomial can be written in the form like y of x equals to y0, y0 means 0.9320 here, and the second point, it can be written as p delta of y0 here, so 0.0316 p here, and third one, if you will just write here, so plus p into p minus 1 by 2 into the third difference, if you will just write minus 0.0097 here, and then again this difference, if you will just write p into p minus 1 into p minus 2 by 3 factorial into next immediate value is minus 0.0002 here, plus all other term we can just write here. And if it is the question, since the question is asked to compute or taken these terms up to suppose second differences here, so we can just consider these terms up to this one only here, and then we can just write y of p up to second differences as 0.9320 plus 0.0316 p plus p square minus p by 2 since this sign can come as minus here, into 0.0097 here. And if we want to first find the first order differences here, so y dash p, this can be written as 0.0316 minus, so this will be just giving you 2p minus 1 by 2 into 0.0097, and this equals to 0 here. If this equates to 0 here for maxima and minima of this point, then we can just obtain this values as 0.0316, this equals to 2p minus 1 by 2 into 0.0097 here. And finally, we will have this value like p equals to, if we will just solve here, p can be written as 3.7577 here. If you will just see here, p is just giving you this value, then to find this maxima or minima at that point, we have to check d square y by dp square here. So if you will just evaluate here d square y by dp square here, then this is value, it is just giving you directly as minus 0.0097 here. This is less than 0 already. So that is why we can just say that this second order derivative is minimum means or negative means we will have a maximum value at point p equals to 3.7577 here. To obtain the values of x for that p, we have to consider again x equals to x0 plus ph or x equals to a plus ph there. So if you will just consider that to find this x value for this corresponding p value here, so x can be written as x0 plus ph here, or this can be written as a plus ph. So the final value, if you will just see here, that initial value is taken as 1.2 here, plus p is 3.7577 into h is 0.1 here. So finally we can just obtain these values as 1.5758. 1.5758. If you will just see this point here, so this values of x is just observed in this point here on this tabular values. This means that we can have to use this Newton's backward difference formula to obtain this value at that point. So to find this maximized value at that point especially, we have to use this backward difference formula as x equals to xn plus ph at that point. This simply satisfies that p can be written as x minus xn by h there, which can be written as 1.5758 minus 1.6, since 1.6 is your xn value. So we can just write that one by 0.1, this equals to minus 0.242. Since p is lying between like minus 1 to 0 there, so we can just use Newton's backward difference formula. And if we want to evaluate this polynomial at that point, especially we have to consider that yn equals to 1.6, the particular value will be 0.9996 here, then plus p nabla of yn, that is p is just giving you here the value as minus 0.242. So minus 0.242 into this nabla of yn, if you will just see this backward table differences here, that is just giving you 0.0021 here, if you will just see, and plus then p into p plus 1 into p plus 2, sorry, p into p plus 1 by 2 factorial del square of yn here. So p is given as minus 0.242 into minus 0.242 plus 1 by 2 into minus 0.0099 here. So then the final value we are just obtaining as 1.000 here up to 4 decimal places. So then we will just go for this error approximation in the interpolating polynomial case. So for that we have to consider like a Newton's forward difference formula, backward difference formula, or like a divided difference formula to evaluate this error at different points there. So, already we have discussed that these errors that is written in the form like a Rn plus 1 x as Rn plus 1 x, the error term is defined as x minus x0, x minus x1 up to x minus xn f to the power n plus 1 zeta by n plus 1 factorial. Usually this is the error term for the general approximation of this interpolating polynomials we have defined, where this zeta value should lie between x0 to xn here. And if we will just go for this differentiation of this error term here, then we can just differentiate this x product C here separately, and we can just take the differentiation of this zeta. Since zeta is a function of x here, we can just treating this two variable product form here. This means that if we will just consider this side as omega x here and this side as f to the power n plus 1 zeta by n plus 1 factorial here, then this differentiation with respect to x for this error term, it can be written as omega dash x f to the power n plus 1 zeta by n plus 1 factorial plus omega of x f to the power n plus 2 zeta by n plus 1 factorial into zeta dash x here. So, based on this we can just say that this error, it will just occur at a different polynomial basis. This means that if you just consider exactly x equals to xj, then obviously this omega x will just give you a 0 value here. Then we can just write this polynomial as Rn plus 1 dash at xj exactly, this equals to omega dash of xj f to the power n plus 1 zeta by n plus 1 factorial here, where this zeta should be lies between like x0, x1 to xn for maximized value within any of these intervals there, and minimum value within this interval. Why we are just considering this maximum and minimum value is that sometimes maybe it is just occurring this variable x in the form of fractional form there. So, we have to consider this minimized value for minimized values of x to determine this maximum value of that function. So, that is why we have to consider either it is in minimized form or in the maximized form to obtain this maximum value for this error term there. So, if you will just consider this one in a divided difference form here. So, this divided difference form of this polynomial can be written as, if you will just see this Newton's divided difference error derivation from our earlier lectures, you can just find that Rn plus 1 x term can be written as omega x into f of x x0 x1 to xn there. So, obviously Rn plus 1 dash x can be written as omega dash x into this first product term plus omega x into the derivative of the second product term, and we can just write this one as omega dash x into f of x x0 to xn plus omega x. Since we are just considering the derivative of x x0 x1 to xn arguments, so one more x can be involved inside the arguments. Why it is just coming? If you just see here f of x0 x0, usually it is just written in the form like limit h tends to 0 f of x0 plus h minus f of x0 divided by h here, and obviously this can be written in the form of like f dash of x0 divided by 1 factorial here. Similarly, we can just write f of x0 x0 x0, 3 arguments if it is just placed. We can just write this one as limit h tends to 0 f of x0 plus h x0 minus f of x0 by h there. So, if you just write in that form, then we can just apply this L'Hospital's rule twice, then we can just obtain the second differentiation of f at the point x0 there. This means that if you just see here that h square is just occurring, if you just take f of x0 plus h minus f of x0 by h, so 1 by h product it will be there. So, that is why 0 by 0 form it is just occurring. So, that is why we have to take this L'Hospital's rule to obtain this limit at that position, and this gives you like f double s of x 0 by 2 factorial. So, if suppose r times the same argument is placed, then we can just write that one as f to the power r of x 0 by r factorial. Similarly, we can write if suppose two arguments are equal and all arguments are deferred. So, then we can just transfer that one as f of xr x 0 to xn limit hr tends to 0, since if hr can be placed at that point, then that will just represent the same expression as we have just seen from the previous one. And if you just write in a limiting form there, that can be transformed directly to the derivative form as d by dx of f of x xr x 0 to xn there at x equals to xr, and which can be written as a derivative form with r arguments as 1 by r factorial d to the power r by dx to the power r f of x x 0 to xn there. And if you will just use this expression in the complete derivative term of this remainder term, then we can just get Rn plus 1 dash x as omega dash of xj f to the power n plus 1 zeta by n plus 1 factorial plus the arguments involved for this derivative of f to the power n plus 1 zeta by n plus 1 terms there. So, that can be represented as omega x f to the power n plus 2 zeta 1 by n plus 2 factorial. So, next lecture we will just continue that how we can just obtain this differentiation for the central difference approximations. Thank you for listening the lecture.